Hello, my name is Michel Chammas. I'm a PhD student at the University of Franche-Comté in France. In this research, we are investigating writer identification for historical handwritten document using a single feature extraction method. I'm working with Professor Abdallah Makhoul and Professor Jacques Demerjian. First, I will start with my introduction, then we will discuss our system, then we will discuss the evaluation of our system on the latent historical dataset, and we compare the result with other system. And finally, we conclude with the conclusion and the future work. First, knowing the identity of writer in historical manuscript is one of the most important challenges for humanitarian. As I work in a digital humanities center, we notice that it is a big challenge for the humanitarian to compare the writing style and to identify the writer for each manuscript, especially for those historical manuscripts, and because a lot of them have some physical, bad physical aspect due to the time. Also, they require a considerable amount of time and effort to identify a large number of manuscripts, to identify the writer and the date. So we started, our challenge was to develop an automated system to identify the writers for historical handwritten manuscript and in different language. So we started by implementing a system based on machine learning, and we tried to make it generalize well on the training dataset in order to be able to use it on different languages and different styles. So a writer identification task can be viewed as a multi-class classification and a binary classification problem. In our case, we are trying to develop a verification system and also an identification system, because in some cases we have some manuscripts that we know who are the writer, who is the writer for those manuscripts, and for some manuscripts the writer is unknown. So the process consists of three main stages. Usually they start by a pre-processing to clean the manuscript and to do some pre-processing technique to the like alignment of the text or of the pages, the images. Then they start with the feature extraction and clustering. They identify some important feature in the document, in the images. And finally, they train the system to do some classification or prediction using those extracted features. So our system consists of the following stages or steps. First, the sampling, where we extract the image patches and the key point via the SIFT algorithm. Based on our research, we tried several algorithms. We found that SIFT is the best because it's invariant for scaling and translation. We will talk about it later. We will talk about each step in detail. Then we label the SIFT descriptor using KNN algorithm. And in the next step, we have the feature extraction using a convolutional neural network, ACNN. We train ACNN network to extract local descriptor for each document, and then we create a universal background model for this set, the training set, which will use it later to generalize the training data. And then we, using this universal background model, we apply encoding to create or generate a global descriptor for each document using the VLAD. And finally, we do the similarity by comparing the document and computing the cosine distance. So first, the first step is extracting the SIFT key point and the descriptor. We extract 128 descriptor for each key point. And as I told you before, the importance of SIFT is that it's invariant to the transformation. So then we, at the center of each key point, we extract a 32 by 32 patch, and we label them using KNN by clustering them into groups. And after that stage, we do a normalization. We do using PCA, principal component analysis, and using whitening, applying whitening to PCA in order to improve the recognition performance and obtain a compact representation. So we reduce the dimensionality of the vector, of the feature vector from 128 descriptor to 32 descriptor. So in this way, we decrease the processing cost of the clustering operation. And for the clustering, we apply the mini-batch k-means. We took, in our case, we took 15,000 descriptor, and we group them into 5,000 descriptor each cluster. And we use this cluster to label those patches, to label the patches that we have extracted, and to identify them with the descriptor. Then we use those descriptor and those patches to train the convolutional neural network, ACNN. So we took randomly from the millions of extracted descriptor, we took a sample of 990,000 patch, and we divide them 90% for training and 10% for testing. So in this stage, we applied the ResNet 20, and we do the training, then the validation. After extracting, after doing the convolutional neural networks, then we extract the local descriptor. The local descriptor have a dimension of 64 descriptor for each document. So in this way, we create a universal background model for each document. And then we apply k-means. We apply k-means to create the UBM by choosing by clustering 100 centroid for each descriptor. So we have an array of dimension of 64, and for 100 centroid, just mean we have a big array of 6,400 descriptor. So we do an L2 normalization at this stage. Then we generate the global descriptor for each document by applying the encoding using VLAD. So we aggregate the local descriptor of each document. As I told you before, we have 100 centroid, and each array is 64. So we get a 6,400 global descriptor vector. In this approach, in the encoding, we used a multi-VLAD. We used five VLAD encoding, 5 codebook. And finally, after doing the VLAD for 5 different codebooks, we concatenate them into one global descriptor. So 6,400 times 5, it's 32,000. The dimension is 32,000 for the descriptor, the feature. And finally, we reduce the global descriptor using the regularized PCA. And we extract only 3,200 descriptor. And finally, we compare the documents by using the cosine distance between the VLAD vectors. In this way, we try it for the training data, for the training data set. Then for the testing data set, at the level of the encoding, we use the VLAD codebook or the global descriptor extracted from the training data to extract the global descriptor for the testing set. And to evaluate our system, we choose a latent historical dataset. We choose the ICDAR 2019 dataset, and we compare the result with other system. Here in this dataset, we have for the training data 1,200 images from 520 writers, and for testing data we have 20,000 images. So some of the images, around 7,500 images, are from anonymous writers. So some writers have only one page, and 9,500 images are from where some writers have 3 or 5 pages. So we compared our result with the competition of ICDAR 2019, and we got the best result compared to the other system. We can see here we have 97% accuracy and 91.2% for the mean average precision, which defines the rank of the system. So we have the best single method feature extraction. Some of the team have used the Scoot team from China. They used 3 systems. 2 of them using single method by using also SIFT, but we got a better result from their SIFT system. And the second one by using the Pathlet, by extracting the Pathlet as a feature. And also as a third system, they combined all the 3 together, and they get a little bit a better result, 97.4 accuracy and 92.5 for the mean average precision, with a slightly better improvement, but by combining 2 methods, which require more processing and more time, cost more resources. So using a single method, our system has surpassed all the other systems. Then to validate our system more, we have participated in a second competition. This time, the ICF-HR, it's the latest competition in this domain, the ICF-HR 20, which investigates the performance of a very large scale of fragment document. Here we have a fragment, and the data set was very, very large, around 1,000 images for the testing and 20,000 for images for the training. And we got the first position in this competition. Our system got the best result. So in conclusion, our system have showed a great performance on the latent historical dataset and surpassed all the other systems without any pre-processing technique and with using only one single feature extraction method. For the future work, we will test our system, as we said before, on Arabic historical dataset. And also we are planning to implement and improve end-to-end deep learning system in which we use the deep learning to create a one-shot result without using three system or the three steps from the sampling, the feature extraction, and the training. So we use a one end-to-end deep learning system to get the result. Thank you.